So now we're going to be using the instrumental uncertainty sheet. These kinds of sheets I think are kind of useful at the beginning of the lab, but hopefully once you get used to the idea of what these sheets are trying to show you, will be less and less used as time goes on. Again, these sheets are meant to be tools. They are not something that you have to turn in with each lab if you can present your argument in a way that doesn't require them. Okay, so in this case, the thing that we're measuring is the speed, and the instrument that we used was the speedometer. Now, most speedometers don't actually have divisions all the way down to the 1 miles per hour. Some do, some don't. In the case of your friends, it's actually at 5 miles per hour. Oops, wrong place. And the question is, do you think that you can actually estimate smaller than this? And we're going to argue yes. We think that we can go down to 1 mile per hour. But there may be some times where we're actually going to have an instrument that we use with less precision than we imagine. We're not going to worry about that because we're on a car trip. It's short. We got to get this done. So we're not going to worry about this question. Okay, so do we have statistical uncertainty? Well, yeah, we saw that. We saw that when we measured this, we saw some variation. It wasn't exactly 70, it was about 70. So the name of the variable measured is our speed. And we took 5 measurements. And the sample standard deviation was 2.49 miles per hour. And you're looking at all these boxes and saying, do I have to fill this out? And the thing is, no. You only have to figure out one of these columns. So you could say that you only want to be 68% confident, in which case you would only fill out this column. If you want a 95, you'd need the middle column. And if you really want to just cover all bases, you're really not wanting to be wrong, you could do this at 99.7% confidence. But you only need to pick one of these columns. It's up to you. I recommend sitting right at the middle at 95% confidence. You're going to be wrong about 1 times out of 20. And that's acceptable. It's a statistical variation that you would expect to see. So the thing we need to find first is what is the confidence coefficient for one measurement? 1. Now, you don't actually care about predicting what the velocity of your friend will be at any one time. So you're looking at their speed and you're trying to predict what their speed will be for one other time later. That's not something you're interested in. You're interested in using their mean value and understanding how much that mean value changes and making predictions off of that. So you won't actually need this top row either. So let's just go and eliminate all the things we don't need. So really this big box of 9 individual places has now been shrunk down to only 2 things that we really need to calculate. We need to find the confidence coefficient, or CC for the mean value, and then we need to use that and our standard deviation to find the uncertainty. How do we do this? You know that you can find out the uncertainty in a value by taking your confidence coefficient and multiplying it by your standard deviation. The question is, how do you find your confidence coefficient? There are 2 listed down here. Well, we already said that we're interested in the mean. So if we look this and we read the formula for the uncertainty in a single measurement is typical of the sample. So this here is the formula for single. And that means, and for the uncertainty in the mean of the sample, that this equation here is for the mean. Notice it's got this n minus 1, or the degrees of freedom. We're taking, in essence, the uncertainty for a single thing and dividing it by the square root of n minus 1, because when we care about the average, we end up being able to knock down some of that statistical uncertainty by using more data points. That's what that n minus 1, square root n minus 1 ends up meaning for us. Luckily for you, you've already used this t inverse function many times. So many times. So you've already got it memorized for the confidence level that you're interested in and the number of data points that you have. If you're finding yourself listening to this and wondering, well, how do I actually do this? Don't worry, it's something that we will go over in the first lab. If you've got Excel or OpenOffice or any variant thereof, you can start to play with the t-inverse function yourself a little bit. It just requires knowing what confidence level, some value between 0 and 100 you want, and how many sample points, the n, that you want to use. That's it. Those are the only 2 numbers that you plug in using this formula that it has here, and that'll allow you to calculate the confidence coefficient yourself. Okay, so for your 5 data points, you know that the confidence coefficient is going to be at 95% confidence, 1.24. Now, this is something that doesn't have any units on it. It's just a number. It's just some constraint as to how confident you can be in your data if you only have 5 data points. If you had more and more and more data points, then the smaller you should expect this number to grow. Now you're going to take this and you're going to multiply it by your sample standard deviation. Your sample standard deviation does have units. It always is going to have units. So the uncertainty will also have units. So CC for mean value doesn't have any units, but uncertainty does. And the uncertainty is going to be the same units as whatever your sample standard deviation was. So I'm just going to take 1.24 and multiply it by 2.49, and I'm going to get roughly 3 miles per hour. So then the question is, how much total measurement error do I expect? Looking at this equation, you know that you're going to combine both of the instrumental uncertainty and the statistical uncertainty, so that your total uncertainty on the velocity is going to be the square root of the sum of the squares. So in this case, the instrumental uncertainty was just this thing up here. It's just going to be 1 mile per hour, and we're going to square that and add to it the uncertainty that we got from the statistical uncertainty, which is 3 miles per hour squared. Do the math on that, and that gives me that my speed has an average value of 70 miles per hour plus or minus 3.64 at 95% confidence miles per hour. Now, sometimes it could be that we don't have any statistical uncertainty. We only measured once, in which case we wouldn't even need to do this step. We would just take our instrumental uncertainty and plug it down in here. But it also means that we don't have any confidence interval. We don't really know how confident we can be in our instrumental uncertainty unless that's something that is provided for us on the instrument itself. In the case of the speedometer, it's not really given to us at all. There also may be times where you don't necessarily have an instrumental uncertainty that is very large, so your statistical uncertainty is much larger than your instrumental uncertainty. So then maybe you ignore that instrumental uncertainty because this is math, and who wants to do extra math? Now you'd think we're done. If we found out the instrument, what other instrument do we use? Well, you did have another instrument, and it's something that can possibly be overlooked. And this is something to keep in mind in the actual lab. Sometimes we use instruments without even thinking about it. In this case, the instrument was the sign. The sign that told us that we were 57 miles away from our destination might not have been right. Now, when we're asking ourselves questions about how we use this worksheet to evaluate the real world, it can be a little squishy. That's why these questions are here. These questions want you to think about why you're using the instrument. Once again, these worksheets are designed to help you. They're a tool. If these questions become burdensome to you, you don't have to answer them. You don't have to deal with them. But in the case of the sign, these questions actually provide us a way to think about how we use that sign. Now, what is the smallest division of the instrument on the sign? The sign didn't say 57.3 miles ahead, and it didn't say 60 miles ahead. So we are going to say that it's likely that the smallest division is 1 mile. We don't know if there's a fraction of a mile, and we don't know if the sign, we are going to argue that since it said 57, that the sign's at least not estimating at the tens of miles. So it's probably accurate to roughly 1 mile. And the question is, do you think we could justify a precision smaller than the smallest subdivision? And it's probably no. I mean, we don't really have, unless we started looking at some other way of measuring the distance from where we are and where we're trying to get, we don't think we could probably estimate that. Now, the other question is, do we think we might have used the instrument with less precision? And I would argue that that could be possible. It could be that we looked up at the sign, we saw 57, we looked at the time, and we're going to use that. But there's some imprecision there. We could have been wrong up to maybe a little more than a mile. It could be that the time when we stopped looking at the clock was also a mile, so this thing could be up to 2. With both of these questions, there isn't necessarily a right answer. There are good answers. There are a bunch of wrong answers, like if I were to write 100 miles up here, the smallest division of the instrument, that's clearly wrong. If I were to claim that I could do something smaller than the smallest division and start saying that I can know this down to a 100th of a mile, that's also clearly wrong. But there's some squish in here. There's some places where you can make an argument as to what you think a good answer is, and that's why this space exists. So that you can justify or make arguments. Okay, so do we have any statistical uncertainty on our sign? No, we didn't. So all this part goes away. So we don't have to worry about all that. That's nice. So our variable is distance, and the value that we're using is 57 miles. And we don't have any confidence on this. There's no way to really gain any confidence at 95 or 99 or any of that uncertainty, so I ignore that part. But I do have uncertainty, and the uncertainty that I have is 1. We're going to argue that we could be off by at least 1 mile in the estimate of our distance.